I don't recall that we used geophone on this one. The thermography on this one. If your floors are at very deep levels, I doubt that you'll pick that up with the thermography.
And how deep can you go with your geophones?
With these systems, you can go quite deep. You can maybe go very deep. We normally say that the distance between individual points should not exceed 50 or 60. So it's probably also what you can measure in the other. We cannot measure the actual locations of the cracks and defects. For that you would have to go to impact echo. But this is a very big, it's a good method for getting a good survey on yourself, and then you can combine later on if you want to be more accurate here.
Did you have problems with false positives?
That's why you need false positive means that you have to calibrate. Calibrate is the answer to that. You need always to calibrate. Yeah. Based on these findings, we concluded that this bridge stake was in not a good shape. So from making an upgrade in load carrying capacity, we recommended that they took this bridge down. This is a full-scale calibration. You can see they've taken away the membrane on the bridge, and they've cut it to take them away in sections. It was the right decision that we took, making the non-destructive testings, which then of course turned out to be very destructive as we took down the bridge afterwards. And what caused this is alkali-silica reactions. Destructive testings. You need to have a sampling for doing either powder sampling or concrete cores, having that taken out. You need to take them out at representative locations. That is of course very important. So you can take out cores with a diamond drill. This is a picture I got from OCC. I've been asking what this guy here is doing. We don't know. And you can take diamond drills and take out dust samples, which you can do a lot of dust samplings compared to the time you use of coring. But the accuracy on dust samples is so much smaller. We're talking, if it's chloride analysis, we're talking plus minus 40%. Underwater, don't forget the areas where you cannot easily see how the condition is. You can do for often it will be compressive strength testings. And also we can do different concrete investigations if you have, and the good thing about cores is that you can combine different test methods and get results in combination. You can use some of it for chloride analysis. This is an equipment, rapid chloride analysis. You can also have titration methods in lab. We can look at the core itself and describe the components and what it consists of, visible signs of deterioration. We can do air void analysis by point counting methods. So you got the air content and the air void distribution. And we can also have thin sections repaired, which are only 20 microns in thickness, so that we, in a microscope, we can look through these.
So do you do the petrographic analysis yourself, or do you send it to an outside lab?
We do it ourselves. We have, I would say, 3.5 petrographers. The half one is me. I previously trained as a petrographer, but I don't use it anymore. But we have 3 persons who are very experienced in petrography, and they work full-time with these things. Petrographic analysis, we use it to evaluate durability aspects and developments in deterioration, control of material composition, and I should say that this covers both macro and micro analysis when we say petrographic analysis. We can control repair and ejection. We can also estimate the concrete compressive strength by looking at the porosity and the point count on the composition. This is a part of a superstructure on a bridge where there was some spalling, and we measured the cover to the reinforcement, and it was fairly big cover, no chlorides, no general carbonation. We took out cores, and we found that we had a cold construction joint in this area, And you can see it's been impregnated with an efflorescent dye, epoxy, under vacuum so that it will penetrate all voids and cracks in your concrete. And what you can see here is this is a reinforcement, and you have the cold construction joint here. And if you use it looking at a UV light, we can be very happy about the concrete cover in this direction, but we have hardly any cover here. And also we had not a very good casting around the reinforcement. So then it did not in many cases take much for corrosion to take on at that place. In the microanalysis we can look at both the aggregate type, distribution, any reactions that would take place, cement, the type, degree of hydration, cement content, has fly ash and microsilica have been used, and how much. In qualitatively not quantifiable, it's difficult to quantify in a microscope. Strength estimate, as said. Water cement ratio we can also estimate to a fairly good accuracy. You need to have some references, and what you evaluate is the porosity. If you have a very light green color on your cement paste, that's a high water cement ratio, and vice versa. So you need references to do so. Trained photographers can evaluate with an accuracy on between 0.02 and 0.05 in water cement ratio, which is actually a very good carbon depth of carbonation, air void content, distribution. Very, very useful. We can also evaluate whether cracks were formed in the young concrete or in the hardened concrete. That is a very strong tool when you want to evaluate what caused the crack. Is it a structural crack? Is it something, deterioration going on? Or is it shrinkage crack, thermal crack from the early age?
So how do you distinguish between them?
We distinguish between them by where the crack is running. If you have cracks that run through aggregates, it's formed in the hardened phase. If it only goes in the cement paste, it's an early age crack.
But that's not necessary. I mean, you could still have load-dependent cracks that don't go through the aggregates, right?
I would not expect so. Then you would have a... No, I would not expect so.
But there is from this morning an example where you said the aggregate was so strong that it doesn't go through.
Well, of course, there are cases where the aggregate's so strong. Yes, and in fact, that's one of the big things with seismic. You get some aggregate interlock, so that the cracks going around the aggregate. There's also fatigue cracking. So, everything is a bit of an art, and a lot of it comes down to judgment and what you're looking at, and the basis of your experience and what you've done and where you've done it at.
You can also say if you don't have a good adhesion between the aggregate and cement paste, of course, then you could easily have, or if it's frost or something. So there are cases, of course, but normal circumstances,
yes,
it would go through the aggregate. We can look at all deterioration, chemical, frost, leaking. These are some pictures taken in the microscope. And remember where air used to be epoxy coated, epoxy is now there, so that's the yellow parts. You can see it's, don't hold my hand and my finger in front of it. So this used to be air voids that are now filled with ettringite. So that's formed because of water going through your concrete. So that's an indicator on frost reactions. This is a crack pattern. You can see it's only in the cement paste in this case. That's a sign of early age frost. You can also look at aggregate gains if alkali silica gel has formed. Very often you can follow a crack and then find the reacting aggregates a bit further down the crack. We can also look at sulfate attacks. This is a special type of sulfate attack called thaumasite. It has, if you go to where you have very low temperatures, high humidity, thaumasite would participate instead of gypsum, and that completely can make your concrete go into solution. This is somebody said it looked like a fried egg. And I completely agree. But this is a glass particle, looks like this from fly ash, and you also have residual carbon, which is also an indication of fly ash being added. When we talk about water cement ratio, average, you can measure an average when they add the water. But if they forgot to pre-wet your aggregate, they might have a porous zone around your aggregate like that. So on this one, the average water cement ratio might be very good, but you could have more or less motorways through your concrete by this, affecting also your durability. Chloride concentration, either from powder or from cotton ground samples from your concrete core. We can measure the average diffusion coefficients over time, and they would be different from those you measure 28 days for durability design. You can measure them after a longer period of time, and you can estimate how long time will it then take before you have an issue, a possible issue with chloride-induced corrosion at your reinforcement depth. As I said earlier today, what causes corrosion is the water-soluble chlorides, but they are extremely difficult to measure. Actually so difficult that we normally don't do it. We measure the total acid-soluble chloride concentration and have that as where we have a rules of thumb for what the threshold values are. Concluding, NDT and destructive testing methods, they are necessary to get insight into both marine structures but all other structures, because you shouldn't implement repairs unless you know what caused your deterioration. Say you have a structure and you have some premature deterioration, you go on and you paint it. If it was frost that caused that deterioration, you have now made sure that the water cannot evaporate. So you worsen the situation in that case. Things like this. So that's crucial. Know what you're doing.